So this is another piece of evidence for my quantum gravity theory, and this is, of course, the fact that the Earth's rotation is slowing down. So if you go back to the time of the dinosaurs, like 230 million years or so ago, the Earth's the length of a day on Earth would be shorter than it is now. So it would be like 21 hours long or something like that. That's how long a day would be. Probably in the Cretaceous period or something like this. And this effect isn't really noticeable on human timescales, though we do measure it, of course. We do measure the fact that the length of days seems to be decreasing. The length of years is also decreasing. So, in addition to the Earth's rotation slowing down, what's also slowing down is the rate at which the Earth moves around the sun. So, these are two effects which obviously are strongly influenced by gravity and the way that gravity behaves. It is currently put down to the fact that the sun is losing mass, which I guess is connected to this, of course, also. But what it's mostly due to the fact is that the Earth propagates its own gravitational field, or its own gravitoelectric field, if you like. If you'd like to coin a term like that, possibly, to describe this cloud of tunneling electrons, which is in my theory of quantum gravity, propagated by the Earth, that interacts with the cloud of electrons propagated by the sun. So you have one superposition, one classical superposition of two electron densities, one upon the other. And the Earth's rotation electron density spins along with the Earth. So the electrons in space, when they show up there, which they do very, very briefly, those move in the direction of the Earth's rotation along with the Earth. So they move in tandem with the Earth. And these electrons in the electron density interact with one another. They interact with other electrons from the sun's electron density, for example, and they resist one another. So there's always a force of resistance being created by objects in space with other objects in space, or in relation to other objects in space. So there's yeah, and this is the same for the Earth moving around the sun. That's becoming very slightly slower as well. So you imagine this cloud of electrons surrounding the Earth. That's always bumping into the electrons surrounding the sun. So the electrons and those two electrons impart resistance to one another. And this isn't really accounted for in Einstein's theory of general relativity. Space doesn't really have this. Well, it does have this resistive property to it, I guess, in general relativity. I mean, general relativity does talk about stars and so on trapping light around them, and that should really all be accounted for within the context of curved space time. But I think really what we need in a quantum theory of gravity is a quantum to expose why, for instance, space time traps light. And I think the electron is just a very natural candidate for that. I just see it because it interacts with light so readily. It interacts with other particles as well, of course. It can interact with protons and hence create a force of attraction between an electron density and a proton. And a proton will always move towards where there's more electrons. So, this is like quite key to understanding gravity, and that if there's an electron density with lots of electrons over here and a proton over here will move towards the electron density because they're mutually attracted to one another since they have opposing positive and negative charges respectively. And yeah, this is why all sorts of behavior manifests in the universe. It comes down to fundamentally these interactions between electrons and protons and electrons and photons and these sort of different elements of how subatomic, standard model particles interact with one another. So yeah, I just wanted to talk about this. And this resistive property of space, this can also be measured in, for instance, our spacecraft. And we can fire something into a gravitational field, into one of these electron densities, and it will ultimately start slowing down. That's, what happens. And it doesn't stop Newton's first law of motion being correct. An object will continue to accelerate so long as an external force isn't acting upon it. We know that an external force, these clouds of electrons, are acting upon external bodies, so we can recover classical physics notions this way. And we know that yes, objects moving through space do slow down. They don't keep going at like whatever speed they were given to begin with. But yeah, so um, that's how I understand these phenomena of the Earth slowing its rotation, slowing down, and years slowing down as well and becoming longer, because yeah, the Earth will ultimately just keep rotating around the sun, keep moving through its electron density, keep moving through this molasses-like cloud which underpins everything, and yeah, it will slow down as a result of that. And we find this also with slower rotation curves closer to the centers of galaxies, closer to the centers of black holes in galaxies. So this gives us a great deal of insight into the dark matter problem, and it's a combination of two things really. It's the combination of an electron density trapping radiation, and ultimately that radiation pressure creating a resistive force. So that's one way of looking at this also, because when electrons repel one another, they exchange photons with one another. So in any case, it always comes down to radiation pressure. It always comes down to this pressure between photons and electrons. And that's because that's what happens when electrons meet. And we can, yeah, think about it in terms of radiation pressure very much also, since you can say that, well, the sun's mass is being lost as radiation pressure. So it's losing electrons, it's losing protons all the time, even. Those are coming out of it in terms of cosmic rays. It's losing neutrinos all the time, and those have a very small amount of mass, and it's losing light all the time as photons, which likewise have a very small amount of mass, I believe. And I think relativity would agree with me on that. And yeah, it's the combination of all these different forces constantly acting on the Earth, propagated within an electron density, that causes, for instance, the Earth's rotation around the sun to slow down, because it's moving through all these particles in the background, all these particles that we're very familiar with, that we understand via the standard model of particle physics. And it's like a soup or a sea of particles that the Earth has to move through. And the Earth has quite a great deal of momentum, going around the sun. It moves very fast around the sun, and it rotates very fast as well. But yes, this is ultimately slowed down due to the mutual interactions between the Earth's particles and the background particles. So, yeah, that's one way in which we can begin starting to understand the effects of gravity, really, from a particle physics perspective. Thank you for watching. I hope you enjoyed this video. Bye.